So in this video we're going to discuss the homology of a closed orientable surface. So we've already done the case for torus. So torus is a closed orientable surface of genus 1. Now we're going to do general genus. So let's just recall how these surfaces look. Here's a surface of genus 3. Okay, so we just basically take three tori and kind of join them together like this. That's a closed surface of genus 3, but then we can also do these by gluing. This is discussed in the knots and surfaces course. So here we'll do the gluing diagram for a surface of genus 2. Okay, so what we do here, we have an octagon to start with. So here's an octagon, and this is, you're supposed to think of this as being filled in, and we're going to mark the edges. Okay, so this edge we're going to call A, and then this one is B, and then we have A backwards, and then B backwards. Then we have a C and a D, and then we have a C backwards and a D backwards. Okay. So if you take this octagon and you glue together the edges according to these labels, so this edge that's called A gets glued to that edge that's called A, this edge that's called B gets glued to that edge that's called B. If we do that, then we end up with a surface of genus 2. Okay, so I'm not going to explain how that works. You can just believe it, or it was discussed in knots and surfaces. Okay, so this is okay. And so we can we've got the surface X, say, of genus 2. We'll call this guy X, and we're going to divide it up into two open sets, U and V, pretty much the same pattern as we did for the torus. Okay, so our U. So my U is going to be the kind of outer part where we just make a hole in the middle. And of course, we've still got the same gluing on the edge. And our V is going to be just a disc in the middle, which kind of slightly overlaps with that, so that the U intersect V, it'll be an annulus like this. So we need to understand the homology of these spaces. Okay, so again, V is going to be contractible. And as our U is homotopy equivalent to a circle. We're going to call this loop here little u. Okay, so your H1 group is just multiples of this U, this loop going around here. But then it's kind of a bit more of an issue to try and work out what this U looks like. Okay, let's first work out about the kind of vertices of this U. I mean, here, let's call this point P here. So P is the beginning of the edge labelled A, and this is the beginning of the edge labelled A as well, so that's also P. But then P is also the beginning of the edge labelled D, and here's you've got the edge labelled D here, so this one we can also call P. But notice here that this P here is the end of the edge labelled B, So that's the same as this point, right? Because that's also B. Uh, and also this, we're seeing here that P is the end of this edge labeled C, and this one is also the end of C, so that one's also P. But now, yeah, we see that P is P, so P is the end of C. P is also P is the end of D. Okay, this is a D here, and the end of P is end of D is P. So the end of this D is also P. Okay. And yeah, and then this P here, that's the beginning of C, and so this is also the beginning of C, so that's also P. And now this P is the beginning of B, and this point here is also the beginning of B, so that's also P. So we see that when we do all these gluings, all these 8 points around the edge of the octagon, those are all equal at P. And so what happens when we look at these loops? So here we've got our P, and then we've got our A. So A runs from P to P. And then here's our B. It's also running from P to P. And our C is going from P to P. And same with D. Okay, so if we just look at the edges running around the outside of U, then what we get is just this kind of wedge of four circles joined at a point, which we were calling W4. Okay, we discussed earlier the homology of spaces like this, and we called it W4. And so this is kind of if you just look at the edges, you kind of get your W4, and then this kind of band here gives you a sort of fringe attached to that. But the fringe doesn't actually affect the homotopy type, because you can you just push the fringe out onto the edge. That gives you a kind of a homotopy showing that the inclusion of the W4 in your U is actually a homotopy equivalence. So we find that the homology of W4 of U, so it's the same as the homology of this W4. So in degree 0, you've got Z. In degree 1, well, you've got 1 Z for each of these loops. And then beyond that, you've got nothing. Okay, so now we're in fairly good shape for trying to think about the Meyer-Victoris sequence. But one key question to ask is about the. It turns out we have to think about the map from map I lower star going from H1 of U intersect V to H1 U. Okay, so let's just write that in this little box here. So we've got so here we've got just ZU as the homology here as H1 of that group going to and so we need to understand what is this map I lower star here. And it's more or less the same story as with the torus. Okay, so we've got this loop U, which we can draw again over here. And this is homotopic by a loop homotopy to the path that runs all the way around the edge. So that goes from U to all the way around the edge, and you've kind of got a join of paths, but join of paths corresponds to addition of homology classes. So you get A plus B, but then you get A backwards, which counts as minus A. B backwards counts as minus B, plus C plus D minus C minus D, which is 0. So we see that this map I lower star from the first homology of U intersect V to the first homology of U is just the 0 map. Okay, so now we're in good shape to do the Meyer-Victoris sequence. Okay, so let's just remind ourselves where we've got to. So we've got our X as our surface of genus 2. That's going to be U union V, where and actually, and so I've kind of drawn pictures of the case where we had a surface of genus 2, but I'll write up here what works for a general genus because it's pretty much the same. Okay, so we had that. So our H star U, so U, we've got a Z in degree 0, and then in the pictures we had we had a Z4 for H1, but in general that was it's going to be 2G, right? So G is the genus. Before we had pictures for G equals 2, and you had a Z4 here, but in general it's going to be Z to the 2G. And V was contractible. It's just a disk. And U intersect V was homotopy equivalent to a circle, so you just got Z and Z like so. And and our I lower star is 0 as a map from H1 U intersect V to H1 U. So Majorvic torus sequence, the truncated Majorvic torus sequence, is going to be like this. You get your H3 U intersect V, H3U plus H3V, H3 of our surface, and you get H2 of our surface here, and then we have our H1s, and here H1X, and we're doing, because everything is connected, we can do the truncated version in which we just get a Z, get a 0 there. Okay, so what do we know about these various groups? Well, U intersect V, of course, we know we've got a Z here. Okay, and then but then you've got nothing above that because it's just a circle. So we've got 0 here, 0 here, and then over here for our U again we've got Z to the 2G for the H1U and nothing for the H1V because V is contractible. So here we've just got our Z to the 2G. And then here's the X's, that's what we're trying to find out. And then here you've got your H2 of U and U and V, but certainly H2V is trivial, H2U is 0. Yeah, we don't have anything more in this column, just got zeros everywhere. Okay, so now, and then here we've got our I lower star, which is 0. Okay, and so because this is 0 and that's 0, exactness forces this to be an isomorphism. And then because this is 0 and that's 0, exactness forces this to be an isomorphism. Okay. And then because this H3X is sandwiched between a 0 here and a 0 there, this group is going to be 0. And similarly, the further groups are going to be also 0. So we find the homology of X. Okay, in dimension 0, I mean X is connected, so we just get a Z there. And then our H1X, well, this map here is an isomorphism. So this our H1X is just a Z to the 2G. And then for our H2X, so this delta here, as we said, that's forced to be an isomorphism because of this 0 and this 0. So delta is an isomorphism, so H2X is isomorphic to Z. And then our H3X is 0, and then the subsequent one's also 0. Okay, so this is the answer for the homology of a closed surface of genus G.